Now, magnets were, again, discovered in the ancient world. They got their name because the place they discovered them was an area known as Magnesia in Asia Minor, somewhat east of Greece. It was weird lumps of dark metallic rock. It was crumbly. As it crumbled, the crumbled pieces would actually be attracted by the original rock. And so for a while, people grouped electricity and magnetism together, not because of cause, but because of effect. Nobody really thought that magnetism and electricity had any real connections, but they had similar outcomes. They each attracted small particles. When we play with magnets, we discover that there are some real similarities and some differences. I have marked the side of these guys that points north with red. And that was discovered early. When they put lumps of this magnetite on cork and floated it in the water, they found that it rotated on its own until it pointed north. They invented the compass. So the north end of each of these magnets is in red, and we note that the north end of this magnet causes the south end to come around, but if I try to fool it, it knows. It knows, and it switches, and now the north end is attracted to this south end. But if it thinks it's all right, I can switch, and if I do this at the right rate, I can make that guy turn without touching it, because we can deliver forces through fields, okay? So that's a lot like electricity. Like poles repel, unlike poles attract. But very much unlike electricity, I can't just have one pole. There's no such thing as a north magnetic pole. I have to have both. I have to have a magnet that has both. So that's very unelectrical. I don't, electricity I can have monopoles, but magnets I always have dipoles. So I've already alluded to the possibility that magnets create fields. And so one of the standard things, we're doing this kind of high-tech, but you can do this very easily on your own. Get a sheet of paper, put it on top of a magnet. What we have is a magnet that we glue to the bottom of a petri dish, and we place that magnet here on an overhead projector so you can see it silhouetted, and your vision isn't failing. We can actually focus the overhead projector. Okay? Now, I then have a pepper shaker that is filled not with pepper but with iron filings. Okay? It makes your food really crunchy. Okay? But if we shake iron filings out here, we find inexplicably that randomly shaken filings land in a very unrandom way, and they line up in such a way as to say that the two ends of this thing are pretty important, and along with being important, they seem to have some sort of interaction. If this were bigger, if I did this with my monster magnets and I took a compass needle, I would find that the compass needle in any position pointed in the same direction as the lines that we have there. And in fact, we end up defining magnetic fields with compass needles. We say a magnetic field points in the direction that the compass needle points. Since opposite poles attract, we find if I put a compass in here, the north end of the compass points to the south end of the magnet. And so the magnetic fields point away from the poles, points away from the North Pole. Okay, we find another interesting thing. Early on, we can bring the light up, some experiments were done where, and people were constantly trying, this is pure research. This is the research that sometimes we have trouble justifying in science. It's kind of just, let's play around and see the way things work. And the problem with that is that everybody wants to know, well, what's it good for? And the answer is we don't even know yet. Unless we figure out how it works, we can't tell you how to use it. And so we need to pay, at least in the beginning, for experiments that don't have guaranteed outcomes. And so early on, that kind of work was done where people said, well, electricity and magnetism, they have some similarities. Why don't I take a wire with electricity in it and put it near a compass? Now, a compass was an early scientific measuring device. And the reason is that in order for a compass to work, you need to set up a device that senses very small forces, because the Earth's magnetic field is very small. And so this compass needle can detect a tiny amount of magnetic field. And so they took a wire and put it next to the compass and ran electricity through the wire and found that the compass all of a sudden started pointing in a different direction. That indeed electricity in some way affected magnets. They found, if they did it the other way, that if they put the compass on top of the wire instead of under the wire, it also got deflected. It got deflected the other way. And so that was kind of confusing. There really wasn't any consistent behavior, and they weren't quite sure how to handle it. That was until they decided the experiment had to be done, and remember I said this early on, in 3 dimensions. You just can't do this on a flat tabletop and get it to make sense. And so we're going to do this in 3 dimensions. So we've got, in essence, a flat surface here that our magnets are free to move in. But we've got our wire running not left or right, front to back, but it's running up and down. That's a 3rd dimension, right? Are you with me on 3 dimensions? First dimension is left, right. Second dimension is forward, backward. 3rd dimension is up and down. And now, because these are big magnets and the distances are pretty great, we can't use a D cell. We need to get serious. And we got serious by getting a really wild power supply that gives me 150 amps of electricity. I should point out that 20 amps is enough to blow a fuse in your house. Okay, so this is more than 7 times that amount of current. The wire that we're running through, this is a single wire. This is not a bundle of wires. It's one cover of insulation, and the wire itself is about a ½ inch thick. And so please note that the positive here, okay, typically in technical devices, positive is symbolized by red. So the positive side of this electricity goes through this wire. It goes up, over, and down. We are going to say that that is the direction of conventional current. Conventional being the way Ben Franklin talked about it. Today we know that what actually happens in the wire is that it's not positive guys going this way. It's negative guys going that way. Okay? It turns out that it doesn't change anything. Because remember, if I reverse the sign and reverse the direction, I've got 2 negatives. Right? And 2 negatives make a positive. Okay? Double negative. I ain't never doing that again. Right? Did you ever take that apart? There's 2 negatives. It means I'm going to do that, doesn't it? It doesn't mean I'm really not going to do that. I mean, that's what you want it to mean. I just said no twice. Well, no. When I say no to no, that means yes, doesn't it? Okay? And when I say, okay, opposite charge, opposite direction, I'm back to canceling out. We're going to use conventional current because we are the University of Pennsylvania, and it's the way Ben Franklin did it. And at Penn, you do not diss Ben Franklin. Okay? So it comes up, over, and down. Now, it turns out we're not the only ones, and we're going to show you why in a minute. But let's turn on the electricity and see what happens. Okay. All right, so this is on. We're going to get positive electricity going down. Okay? And here goes. Whoa. Like there's an amazing force field there, except it doesn't make sense. If it's a force field, why don't they both point at me or both point there? One of them points this way, one points that way. How do we even talk about that? Well, we don't really have enough information, but I couldn't afford more magnets. So let's take this magnet and move it. Notice I'm not going to move my hands in. I'm just going to change position. I'm not going to change the way. So I'm just going to bring it this way, and look, it's moving on its own. It doesn't want to point over to the wall anymore. It's pointing at the blackboard. What if I bring it over here? You got to get it in here. And look, it now wants to point out towards you guys. Okay? So what's happening? Is there a single way to talk about what's happening? And the answer is, it looks as if they want to point circularly. Right? This guy wants to point here, that guy wants to point there, this guy points here. Okay, so how do we, is there a way to describe that? Well, we're stuck in this horrible three-dimensional situation, and the way to describe it is with our right hand. Because the current is flowing down, let's take this down, and if I have my thumb in the direction of that, the fingers of my right hand curl just the way the wire wants to go, or the magnets want to go. My fingers back here are pointing that way, that's where that magnet's pointing. My fingers over here point that way. And so my right hand will do that. My left hand won't do that. If I put my thumb down, my left hand points this way, unless, of course, I've pissed off the mafia and they've broken all my knuckles and my fingers bend both ways. Okay? But for most of us who have been sensible, okay, our fingers only bend one way, and we actually can use our hands to determine an orientation of three dimensions. So this is why Ben Franklin's idea has stuck, because you loser left-handers are in the minority. Okay, most of us are right-handed, and most of us want to use a right-hand rule. If we use negative current, it in fact is a left-handed rule. If we want to say, well, electrons go this way, then we have to use this, and that points the right way. Okay, but the right-hand rule has become kind of the way you do electrical engineering, and so conventional current still gets referred to, even though we know that the wire is doing things kind of in reverse.